All right, everybody, welcome back. We are now in day 6 of the newest and last unit of the school year, all about the universe. And we've been getting into some stuff about dark matter and dark energy as well. So for question number 1, as you can see here, what is the composition of space? Specifically, what is space made up of, right? What does it consist of? Then number 2, what evidence is there for dark matter? How do we know it's there if we can't necessarily grab it or hold it or feel it or see it, right? And then 3, what is dark energy causing in our universe, right? What's it causing? So I'm going to give you some time for that. But let's go ahead and had it on page 9, right? Let's see our answers. I've got some quick video clips I'd like to show you about these topics as well here in a moment. But for number 1, understand that space is going to be, for number 1, guys, 4% normal matter. That means only 4% of all of space consists of stars and planets, right? Whereas the rest of it, 25% dark matter and 71% dark energy, right? So think of space like an ocean of darkness, right? Think of the stars and the planets like the fish and the darkness like the water. That's essentially what it is. Pretty cool stuff there. Pretty cool stuff. Then number 2, how do we know dark matter is real and exists? Well, 2 things. We assume it's there based on how gravity works, right? If there wasn't dark matter and we looked out into space, we'd see the stars bouncing around and flying around all over space, right? But they don't. Relatively speaking, they sit still and move very slowly, almost as if they're like sitting in a liquid or like a jello, right? That is dark matter. Not only that, guys, when we shoot light beams into space, the light beam doesn't just go straight permanently, right? The light beam, we've seen in many cases, actually bends and bounces around other parts of just empty space, meaning that there isn't just empty space, there's dark matter sitting in empty space. Let's see some more details with that before we get to number 3 with our first little quick video clip.
This is a puzzle that is being put forth by the universe to us, and I cannot think of anything else better to do with my time than to try to answer that puzzle.
Even though we haven't seen it yet, there are a few key pieces of evidence we have found so far in the search for dark matter that tells us we're on the right track.
We are certain that dark matter exists because the evidence for additional mass in the galaxy is all over the place in astronomical observations. You can see the gravitational pull on stars and on galaxies, to even a lot more subtle things, like you can see the relativistic effect of invisible clumps of dark matter causing light rays to bend.
Most recently, there have been beautiful observations using optical data and X-ray data, looking at gravitational lensing to infer the distribution of matter in colliding clusters of galaxies.
But by far, the smoking gun for dark matter is the cosmic microwave background. This is the earliest thing that we can see through our telescopes through light.
It's basically a photograph of a moment in history after the Big Bang, when the universe was only 380,000 years old. It also shows temperature data, and when we measure the fluctuations in temperature, the position of the peaks can determine the ingredients of our universe. It shows that less than 5% of the total mass of the universe is made up of what we call normal matter, like visible stars, planets, and galaxies. Then 26.8% of the mass of the universe is dark matter, and the rest is made up of dark energy.
If you ask me what dark matter was, I'd say, I have no idea. If you ask me what dark energy is, you wouldn't be able to show that because it would be, I have no bleep, 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 bleep idea.
Which means we should just leave dark energy for another day. Now,
Okay, so as the video kind of stated there,
dark matter exists.
and I know the percentages are a little different, and I kind of rounded those numbers out too. So as long as it made more sense from that point of view, but yeah. So let me go back here, this part of the video, right? If there wasn't dark matter, hold on. If there wasn't dark matter, right? All of this radiation would spread out evenly in space, okay? So you see that, this is just a little snapshot of a part of space, right? It's showing us the radiation. So the orange stuff would be evenly spread out. But in this case, we see pockets of blue throughout the radiation. those are the parts where the radiation is going around the dark matter, right? So major evidence that there are more dense, darker parts of space where that dark matter is sitting, right? And then we'll also get into gravity, right? This is the stuff that holds up the planets and the stars throughout all of space. It's the reason it doesn't fly and bounce around everywhere. They're kind of sitting still in a jello type material. It's that dark matter. The thing about it is, guys, is that it's so inconceivable to our senses that it's kind of beyond our senses, but we can see it's there through other lines of evidence, right? And then our last question here, guys, number 3, what is dark energy causing in our universe? It's going to be causing the universe to expand. The universe is expanding. There's some force of energy pushing all the galaxies and the solar systems further and further outward. So let's kind of get a glimpse of that through this video here. Oh, 1 second.
And then bubbles keep popping.
I'm going to start this again. I'm only going to play different sections of the video.
So 20 years ago, by looking at supernovae, astronomers noticed that the universe wasn't just expanding outward, it was actually accelerating faster and faster outward. Not even the explosion of the Big Bang could have set this in motion. And they began to think maybe space itself is expanding. But saying space just is special and expands is kind of random. It's like having magnets and seeing them attract and just say, okay, magnets attract, and not worrying about electromagnetism or the fields involved. Now, remember, in Einstein's view, space-time is basically this mesh that just sits there unless energy or matter bends it. And you might have seen videos or images of the bending of that space-time mesh that causes things to attract. But maybe there's a special kind of substance, something invisible and undetectable, that pushes the space-time mesh apart. Imagine that space is full of bubbles that repel each other. And whenever there's enough space for a new bubble to form, it does. And that bubble repels all the other bubbles. And then bubbles keep popping into existence, pushing each other apart, and pushing space with it. So space and time probably isn't made of...
right? We know that dark matter exists. Why? Because you see we're kind of here, the planets and the stars kind of sitting in something, right? They're sitting and they're not flying all over the place, right? So this is kind of that dark ocean of darkness I told you about, right? We can't grab it or grasp it or conceive it with the human senses, but we know it's there through other means, right? And then we look here, the dark energy, we see these virtual bubbles with the dark matter. They keep multiplying and expanding, and that's what we call dark energy. That's what's causing the universe to expand further and further out, right? Okay, so let's go ahead and move on. That's pretty what we said for the Go Blue, right? So universe is expanding. Table of contents is 9 through 10, the Doppler shift and effect. Today we'll go over 2 practice questions, which you may see on the future online test. So do your best on that. 9 and 10, Doppler shift and effect will be today. So 10 will be what we get to with the majority of what we have today for our material. All right, and let's go ahead and be ready to answer these questions in the chat, guys, for your credits for participation. Question number 1 today. We will do 2 questions today. How was cosmic background radiation first discovered? This is on page 7 if you guys are stuck. Again, there's 2 right answers here, but one that's the most kind of just specific general answer. Was it first discovered, again, is A, Bell Labs antenna, B, disrupted radio signals, C, WMAP, or D, Doppler radar? Pick the best answer. Please answer in the chat. You guys have 30 seconds. Answer in the chat. You guys have 30 seconds. Okay. While you guys do that, I'm going to go ahead and update the attendance here. You can answer the question in the chat, guys. A, B, C, or D for participation. A, B, C, or D. If you do not answer, that does not go to your participation. So I got Irina here now, okay? Okay. 15 seconds, guys. We need more answers. I only got one so far from, oh, I got Lakia and Isaac. Thank you. All right. We've got 10 more seconds. 10 more seconds. Okay, let's see our answers here. 5, 4, 3, 2, 1. Let's see. I got Lakia, Isaac, Yorkies, Diego, Sanaya. Thank you for answering. You guys get those participation credits, right? And then for our answer, I think, let's see, only Diego got it correct. It was letter B, disrupted radio signals. A would have been correct as well, but B is your best answer. Again, when you go between radio stations, you hear that static noise. That's what they first heard that made them question, okay, what is that? Later on, they discovered it to be cosmic radiation between those satellite signals, which helped give us the first evidence of the Big Bang. All right, let's move on now to a very quick lesson here. Go to page 10. We're going to go ahead and go to page 10 for today's material. All right, I'm going to scroll back here a little bit. All right, so we need to find out what is the Doppler effect? What is the Doppler effect, right? No need to write any of this down. This is page 10. What is the Doppler effect? What's it all about? Let's watch a quick little video here that kind of explains this from the show, as we know, called The Big Bang Theory. What is the Doppler effect? Just going to play little 1-minute segments of this video, guys, and we'll kind of get to our notes between each segment.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency.
The Doppler effect, as was stated, is the way in which waves are going away or approaching you, right? If the waves are bunching up, the object's going towards you, it's going to increase the frequency. Again, frequency is how frequent the waves are. So for this, I'm just going to have you guys write this on page 10. Again, title page 10, Doppler effect. We're just going to say this. So what is the Doppler effect, right? That's our question for this segment, right? And we're just going to say the second bullet here. So no need to worry about, does it hold it down? I didn't realize that. So what is the Doppler effect, right? No need to write this down, by the way. We're going to cross that off. Is the change in pitch or frequency, it could involve sound, it could involve light, occurs due to the relative motion of a wave such as sound or light as it comes toward or goes away from an observer. Okay, so we're going to put that down on page 10, page 10. Let's go ahead and see an example again. After writing that down, I'll give you a moment for a picture if you need to take a picture of that. And no need to worry about Bazinga, guys. That's just a quote from the Big Bang Theory show. That's just what Sheldon used to say on the show, right? Keep in mind, the Big Bang Theory has now been ended since 2 years ago. So it was the most popular sitcom series in the 2010s, and it ended in 2019, right? Okay. So let's go ahead and move on then to our first example of that with the use of cars.
Frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting.
We'll see an example with sound and an example with light.
So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at
See the
a
sound
higher
waves?
frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch.
All right. So as we just saw for you there, we see the car approaching and then leaving, and we're going to check out how that affects Doppler as well. So the example, guys, is right here. As a honking car gets near you, the sound wave frequency of the horn gets higher, the pitch gets higher, right? So it's like when a car drives by, it's gonna vary and differ in its sound as it goes toward and then away from you. So that's why it gets louder as it approaches you. Why? Because more sound waves are hitting you as the object, right? Getting more sound waves. Whereas when the car goes away, you're going to over time get less and less sound waves approaching you because it's going away, right? One second. Oh, no problem. Thank you for the update. Okay. So the horn frequency gets lower. It's like, and then it goes, right? It goes back down lower, right? Because it's going away. Now, if you're inside the car and you're honking the horn, it's going to sound the same the entire time when you're inside the car because you're getting an even distribution of waves the entire time, right? Because you're not, the person outside is getting the waves at greater frequency than lower frequency. But the person inside the car is getting a constant, steady frequency of waves that are nothing crazy, nothing, it's saying the same the entire time, right? Okay, so that's on page 10 still. We're still on page 10. Let's do our last example before we call it a day with regards to light. How does this affect light? One moment.
That's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future.
All right.
Thanks
So,
for watching.
we've mentioned before the universe is expanding. We know this because all objects in space are in redshift, right? So with that, we're gonna skip this for now, guys. No need to worry about the radar stuff. No need to worry about that. I'm just gonna show a video about it. Okay. So with that, again, Doppler shift has to do with light as well, right? So for light's case, for the stars, when the stars are looking blue, they're moving towards us. When they're red, they're moving away from us. And as it moves back and forth, we see the spectral lines, the color spectrum change. Okay. And this is either red or blue shift, okay? That concludes page 10. Let's go ahead and just to relate it to weather as well, I've got a quick video clip about the Doppler weather system, why it's called Doppler, and how it uses waves to detect how severe rain and storms are. Let's check that out before we call it a day with our last question of the day. So let's just see again. I had notes for this weather part, but I decided we're not going to worry about it for our class today.
A weather radar is a piece of observational equipment that visualises precipitation, such as rain or hail, and it actually looks a bit like a big golf ball on a tee, but inside that ball is a dish or antenna that's rotating around. Radar stands for radio detection and ranging, and as suggested by the name, it's based on radio waves. The dish sends out electromagnetic waves in short pulses travelling at the speed of light. When these pulses hit the water particles, they reflect back to the radar, much like echoes you might hear in a cave. How long the pulses take to return to the radar determines the distance from the radar, and the strength of the returns determines the type of precipitation. This information is converted to data on a map that can be viewed on the Bureau's radar website. A new radar image is produced every 6 to 10 minutes, and these form a 30-minute loop. So it isn't a forecast, but it can be used to see where the rain's been and where it might be heading next. A colour scale is used to indicate the intensity of the rain, black being the heaviest and sometimes indicating hail. The timestamp underneath the radar image is in universal or Greenwich time. This is so that if you're viewing a radar in one time zone and move to a radar in a different time zone, you know that you're looking at the same time. The local time is displayed to the right of the radar image. Australia has the 4th largest radar network in the world with more than 60 radars. These radars are generally located in areas that are prone to high impact weather such as tropical cyclone or thunderstorms that might affect large populations or areas of economic investment such as agricultural or mining areas. There are some limitations to radars. The curvature of the Earth means that the optimal range is between 5 and 200 kilometres. Beyond 200 kilometres, the radar might be showing rain that's falling high in the atmosphere, and this might not represent what's actually happening on the ground. And even in the optimal range, sometimes the radar can show virga, which is rain that's falling but evaporating before it hits the ground. Another limitation is detecting low-level drizzle. This can be difficult to detect because the droplets are small and often
So
fall
as you
close to
see
the
here,
ground
guys,
below the radar's
we not only have sound waves with cars, obviously, but we can see sound waves with our Doppler radar. Again, these buildings that look like kind of like a golf ball on a tee, these are going to detect how dense the rain is, how fast the wind is moving, and where storms are heading as well. All right, so let's go ahead and finish up our lesson today with our last question of the day. Do your best, because it might be on the, might just be on, one second. It might just be on, it might be on a future online test. The question up here, one moment, guys, one moment. All right, so this question I've had a lot of classes today kind of struggle with, so it's a good question to show. But when we talked about the cosmic radiation the other day, right? How do we know it's from the Big Bang and not from the sun, right? So which of these options gives us the best indication that it's not from the sun, that it's from the Big Bang? And all these topics are true, except, again, one only relates to how we know it's from the Big Bang. A, the fact that the wavelengths are microwaves. B, the fact that the universe is expanding. C, the temperature of negative 270 degrees Celsius, so the fact that they're really cold. Or D, the fact that the universe is 14 billion years old. Okay, so go ahead and give me your best answer. A, B, C, D. Get 30 seconds, guys, 30 seconds for that participation. Again, which of these best tells us that cosmic radiation is from the Big Bang instead of the sun? Thank you, Sanaya. Let's do about 15 seconds, 15 seconds. 5 seconds. 4, 3, 2, 1. Okay, let's see what I got here for our answers. I want to thank Diego, Lakia, Yorkies, Joseph, Isaac, Sinai for answering. Thank you very much, everybody. The answer is going to be letter C. So I want to shout out to Lakia for getting the right answer. Again, these radiation waves are much colder than the sun's radiation. It's a big indication that they are from the Big Bang, because the temperature shows that it's been around for billions of years. All right, guys, let me go ahead and double check attendance here. One moment.